Hi and welcome everybody to this talk about differentially private sketches for Jaccard Similarity estimation. My name is Martin, and this is joint work with Anas and Jana, who did their master thesis on this topic here at IT University of Copenhagen. So this is a talk about Jaccard similarity estimation from sketches in a differentially private way, and I introduce all of these things step by step. So first of all, what is our setting? Well, each user has a set of items from a large collection of items. For example, there's a large collection of movies, and users can indicate which movies they've watched. Or there's a large collection of albums, and users can indicate to which albums they've listened to. What they want to be able to do is, so they have these set of albums they listen to, and they want, for example, to find similar users. Yeah, in general, they want somebody to allow to do some kind of similarity estimation on their user vectors, but they have privacy concerns. So that means that they don't want to reveal their actual user vectors. And I'm going to talk about our notion of privacy in a bit. So this talk will have a running example where users can choose to have listened to 6 different albums, and they're over here. Right. How do we find similar users? Our notion of similarity here is called Jaccard similarity. And if we have two user sets x and y, we define their Jaccard similarity in a standard way of being the size of the intersection over the size of the union of these two sets. So for example, when we have the yellow user with these 3 albums and the blue user with these 3 albums, then the Jaccard similarity between these two sets is 1, size of the intersection, over 5, size of the union. So it's 1 over 5, 20%. Users want to be able that somebody can make these estimates, but they want to be able that this is done in a private way. And our notion of privacy here is called differential privacy. It's a mathematical notion of privacy. And let's just maybe dive into some examples. For example, if you use the Google Chrome, you might be one of those users that actually report some information about their websites to Google in an anonymized way, in a private way, and that is actually done using this Google wrapper tool. You can do privacy preserving machine learning, and most recently, and most also maybe with the most influence to the general public, in the US 2020 census, where they go out and ask all of the households in the US certain questions, and they actually thought about using differential privacy because they ought to have a high level of privacy, and differential privacy is, as they put it, the new gold standard in data protection, privacy protection. So what is differential privacy? Well, it's a mathematical notation, and it's a property that a randomized algorithm can have. So in the definition, there's a randomized algorithm M, and it can be epsilon delta differentially private if for each neighboring vectors x and y, and each possible output that the algorithm can produce, we have a certain relation of probabilities, right? So we have neighboring vectors, we're going to talk about this in a bit, x, and M produces some output on x, and we'll see this with some examples. The probability that M produces on x the specific output set should be at most e to the epsilon times the probability that M produces that output on y. Okay, so these probability distributions that are induced by running M, the randomized algorithm, on x and y, make them nearly indistinguishable up to this factor of e to the epsilon. Right, in general, there's also a delta, which is some additional failure probability that the mechanism might have. Okay, but it basically means that if I have as a user have a certain vector, then people won't be able to tell for certain which vector I had compared to neighboring vectors. And here, for the sake of this talk, the notion of neighboring is very easy. Two vectors are or sets are neighboring if they differ by 1 element. Right, so here in this case, yellow and blue, they are neighboring. Okay, There is a central model of differential privacy and there is a local model. We consider the local model where each user does this randomization on their own. Right, so how does this work? In general, what we want to do is that we have blue, yellow and blue, and they want to be able to produce differential private versions of their user sets. And then they want these differential private versions to have some kind of property to be still able to estimate Jaccard similarity to other users. How do we do this? We do a very natural combination of two approaches. We use MinHash to produce sketches, and then we add some noise to make them differential private. Right, so as many of you might know, the standard sketches for Jaccard similarity, a standard sketching technique is called MinHash, introduced by Bourgeat in 1997. And the idea, we also do it with the example here that there is a hash function, and the hash function is just a random permutation of all possible items. Right, so in the beginning there were 6 albums, and this permutation here, from left to right for example, is our first hash function. This permutation here is our second hash function. If the yellow user wants to hash their vector, what they're going to do is they go through this permutation one by one, and the first element that they actually have in their own user set becomes the hash value. So the yellow user would go through the would have as the first hash value this Metallica album, and then we look through the second permutation, and the first element here is this Iron Maiden album. So if we were to use 2 hash functions, then this is the hash value that the yellow user has. Same with blue. Under the first permutation, it's the Iron Maiden album. Under the second permutation, it's the Pink Floyd album. So this is the blue user's sketch, MinHash sketch. Right, and in general we repeat k times to obtain a sketch of length k. Here we do it twice. How do we estimate Jaccard similarity from these MinHash values? It's very simple, you just count the relative number of collisions. Here there is no collision, and there is no collision. The estimate would be 0 over 2, it's 0. While the actual vector set is 0.2. Right. This is our approach to produce these sketches. Now we have to make them differentially private. Because now if somebody says something about, because now if they were to send out these sketches, they would actually tell that, well, I do listen to Metallica and I did listen to Iron Maiden. And that's not what we want. We want some kind of privacy. And the focus of this talk is that we perturb the answer vectors via something that is called generalized randomized response. Right, and here we do it again with the example. What this means is that with some probability, so users go through their elements one by one, and individually they make some coin flips. And let's say with probability 3/4, they would keep the answer. Right, so for example, yellow would do some coin flips and keeps the answer, and I think here keeps the answer, and blue keeps the answer. And let's say this last flip here says do something else, right? And that means otherwise doing something else means that you choose among all of the other items. So now there are 6 different, and among the 5 different albums to the Pink Floyd album, we choose a random answer. And this turns out to be also the Iron Maiden album. Okay. Right, and as you can see, this adds some plausible deniability to these vectors, because the yellow user can just say, well, no, I don't listen to Metallica. This was just the outcome of these random choices. The big question is now that we have these noisy variants, how do we actually estimate the Jaccard similarity from these noisy sketches? Before I show you this, I just want to give you one important little trick here. So here we had like 6 different album covers. In general, we might have 50,000, 60,000, many thousands of items. So we have a large item set. If we then were to apply this generalized randomized response, there would actually be a high probability that we change the answer, or we have to change the answer. And that means that all of this signal is basically lost. So what we do in the paper is that we do something which we call collapsing the universe, where we actually map these, let's say, D different album covers to B different values. right? And we do this at random, but we share this mapping with all of the users. So for example, we say, well, this rainbow album that gets mapped to 1, and then Metallica to 0, and so on, right? Everybody knows this, this mapping. The nice thing now is that the sketch only has, like, each element of the sketch is only a number between 0 and 2. Right, there are only 3 different values, so it's pretty easy to hide, or we don't have to choose that many among such a large collection of elements. Right, if we do this, of course, it seems to be easier to make this private, but on the other hand, it's of course more difficult to find a good estimation. Yeah, because now there are also these collisions. We don't know, was this the AC/DC album or was it an Iron Maiden album? If we just see 2, we have to take this mapping into account. Right, so how do we estimate Jaccard similarity from these noisy vectors? We have these 2 noisy vectors over there, as in the example. We just count, again, how many positions are identical. Here it would be 1 position. We take into account what is the probability that an individual answer has to be flipped. That was 1/4 in the beginning. And then we prove in the paper that this estimate, which is just taking B into account, the number of different items after collapsing the universe, the number C of collisions, the number K of sketches, and this P star, the probability that we choose an answer. This is an unbiased estimator of the actual Jaccard similarity of the original vectors. Right, and often it's of course the question, well, sure, it's unbiased, but how good is the estimate? So a natural goal for us is to get some provable bounds on the quality of the similarity estimation. And what we take into account is, so what do we expect this error to be like of the true Jaccard similarity of the user vectors and our estimate on the noisy versions? We know standard MinHash also has, like the non-private version, has an expected error. It's 1/√k. Like if you were to choose 400 hash functions, then you get a 0.05 error. What we prove in the paper is that if you have, if all of the vectors have at least tau items, and you choose that many hash functions, tau epsilon, theta of tau epsilon hash functions, then we actually get this. So we get that the absolute error is bounded by 1/√, tau epsilon, which is 1/√k, with probability at least 1 minus delta. Okay? It's different than what we get for standard MinHash, because for standard MinHash we get that the larger k is, the better the error, the smaller the error becomes. Here it's more of a, there's a certain good choice of k, where asymptotically it resembles the original error, but we don't say anything for other values of k. Right. There's one last trick in the paper that I just want to show you. So for now, what I told you is you have this individual flip probability. You can easily state what it is. And usually you do this step by step on your sketch. So they make these conflips and you change your answer based on the outcome of these conflips. If we were to do this and we use differential privacy and we do this k times because our sketch is of length k, then the whole algorithm would be k epsilon differentially private. On the other hand, we need a large k to get a good estimation. So if k is rather large, then this k epsilon will be very large, and people would say this is a huge privacy budget they are not willing to pay. What we do in the paper is that we consider that for differential privacy there is not only this epsilon, but there's also the delta, if you look back into the paper. Or you know this from just knowing what differential privacy is. And we consider, like, if 2 vectors are neighboring, and I do this and I use these MinHash sketches, what do I actually expect and to see, like, how many differences do I expect to see in these MinHash sketches when the original vectors were neighboring, right? It's pretty easy to compute with a Chernoff bound. And what we show is if we know this number, that we expect that many differences only, then we can actually make the whole algorithm, then we can split up the privacy budget differently when we in our flip probability, and then the whole algorithm will be L epsilon differentially private and not K epsilon differentially private, but we pay with this delta factor. right? In general, even for small deltas, we get L values that are much, much smaller than the general K. Right. 2 more slides now on experimental results. So I hope you still have this our running example in mind. So we had these albums, and then we would transform them to private vectors, and from these private vectors we know how to estimate similarity, and we also know some bounds. How does this work in practice? Because all of our results were there were a lot of asymptotics involved. Okay, what you're gonna see here is the mean absolute error. That's the error that we got from our similarity estimation on noisy vectors compared to the true Jaccard similarity of the vectors. The experimental setup is that we have 2 vectors. They have a certain size. They have either 50, 500, or 2000 elements, and they are at a certain Jaccard similarity to each other. In the example, it's always 0.5, which is a nice, it's like a worst case instance. Okay, and all of the circles here, they're the 2 vectors. They have 50 elements. With the crosses, they have 500 elements. With the squares, they have 2000 elements. K is the number of hash functions that we're going to use. Epsilon is the privacy budget that we give. And our delta is very small. I think it's 1 in a million. What you can see is that for each different type, we actually have 3 different lines. And these 3 different lines, they are different different sizes of the collapsed universe, right? So there was the original collection, and we mapped them down to B different items. Blue means B is 2, only a single bit. B is 3 for the reddish ones, and B equals 5 is the green line. So what do we see here? What we can first of all see is that this the number of items has a great influence in how well we are able to estimate Jaccard similarity. So if we have only 50 items, then we see our mean error is between 0.35 and 0.5. Jaccard similarity is a measure between 0 and 1. Right, and on average we are like 0.3 away from our 0.5 actual answer. The smaller b, the better in our case. And we can also see that the larger the k becomes, it's actually worse for these input vectors. If we increase the size, our mechanism becomes much better, and we get down to an error of around 0.1. Just to note this, like the error of standard MinHash is 1 over square root of k, so it would be around 0.1 as well for 100 hash functions. Right, you can see there is not that clear of a difference. All of these values seems to work fine. In the analysis, there is some indication that small b values are better than large b values. Yeah, but we don't have like a formal proof for this generalized randomized response that a certain b value is always a good choice. But it seems the smaller the better actually. What we can also see are there are these jumps sometimes, and it's clear to see that with larger k, the error is actually going to increase. Let's look at some very practical examples on real-world data sets. That's a table from the paper, and I just want to walk you through this. Like there's a list of M data sets where users indicate the top artists, their favorite artists, and there's movie lens where they indicate like movies that they liked, and we made different versions with a different number of minimum item sets. We consider like a classical similarity search setting in which we have our ground truth data and we choose queries from the ground truth data, and then we're gonna compute these sketches, and then in the sketch space we're gonna ask for the 10 nearest neighbors or 50 nearest neighbor or 100 nearest neighbors, and we go back and check among these answers was the actual true nearest neighbor included. Yeah, so our 10 means was the near neighbor included in the first 10 near neighbors in the sketch space, which has like these imprecise results. and the same for 50 and 100. There's also this approximation factor, which is just we sum up the similarities of the top 10 nearest neighbors in the original data set. We look at the top 10 nearest neighbors in sketch space, go back to what they actually were in the original space, sum up similarities, and consider the ratio between the two of them. What can we see? In the real world, it's actually difficult. Even if we use MinHash, we get recall add values that are from 0.4 to 0.82 here for the last of M data set, and they're pretty bad, for example, for movie lens by itself, from 0.13 to 0.47, and so on. It gets better the larger the items become. Right. Now, the approach I showed you is this generalized randomized response one, RR, MinHash, and there are always two values. This is the epsilon 4 from before, and this is epsilon 8. And as you can see, there is this factor of 3 here difference. There is a factor of around 2 here difference. So they are quite far away from the MinHash sketches, which are by itself pretty, which can be inaccurate. There's not such a big difference between when we consider approximation ratio, which means that even the results are a bit more imprecise, like the actual similarities that stood behind these vectors turn out to be pretty equal. Right, we see the same behavior as before. The larger the individual vectors become, the better our algorithm, the easier it's for MinHash and the easier it is for our algorithms. We get close to perfect results, for example, here, or movie lens with 500 elements. Right, so this can be used in practice as well. It comes with some penalty, this privacy, but all in all, you get okayly accurate results. That's already all I wanted to tell you. So I introduced these differentially private sketches to estimate Jaccard similarity, and in this talk it was a natural combination of MinHash and randomized response. In the paper we also consider a variant where we add noise from the Laplace mechanism. Seems to perform worse. The analysis doesn't show that in such a clear picture. Right, are more efficient sketches possible? I don't know. As I said before, we kind of match the behavior of a standard MinHash asymptotically, but we do this for a very certain choice of k. And of course there could be other sketches which allow for larger k values. That would be nice. And we did Jaccard similarity, and there are other papers who do this, for example, for Euclidean distance, but I mean there is a whole spectrum of different metrics where you could ask these questions about finding nearest neighbors or similarity estimation under differential privacy. All of the code for the experiments is available on GitHub, and that was it. Thanks for watching.